There's all those, loops, because your head looks, your brain looks like cauliflower. So they want to know where those things were, right? Where is the flesh of the brain, and where is the gap between the fleshes of the brain? The problem is, if you have an X-ray machine, that's all you have, you're kind of screwed, because the gaps are not empty, they're filled with cerebrospinal fluid. And cerebrospinal fluid is mostly water, like your brain, so it looks much the same on an X-ray as your brain. So there's no contrast between the gaps and the brain matter. So they said, we have a great idea. We'll puncture you in the back in your spine, lumbar puncture, right? And they'll drain out all the cerebrospinal fluid from your spine and your brain and replace it with air or helium or something. And then they'll put you in the X-ray machine. And then it can tell the difference, because it's just air, which is much less dense than cerebrospinal fluid. Apparently this is a very painful procedure, so they don't do it anymore. But and sometimes they wouldn't be able to drain it all out, right? So it'd be kind of halfway out of your brain, and the air bubble in your brain is there. And then but they want to image something over on the side, so they have to get you to tilt your head, right, to reorient yourself so that it'll bubble to the top, the part that they want to image. And then they'll image you, and then pneumoencephalography, it's a real thing. Anyway, so X-rays kind of suck. They were very happy to get proper things. All right, so other than X-rays, what else can you do? This is actually also X-rays. Another solution to that problem with the lack of contrast between different kinds of soft tissue is to use what they call contrast agent. I think this one might be iodine. I'm not sure. Anyway, so you can pump iodine or barium into a blood vessel, for example, and then it'll block the X-rays. And then you can tell the difference between the blood vessels and the surrounding tissue. You can do things like this angiogram. Contrast agents, which is kind of cool. There's other things you can use as contrast agents. This one is air. The transparent parts of the intestine here, I think, are air, which makes it more transparent X-rays than it would normally be. And this stuff is a barium slurry, which they administer by an enema, of course, to get it into your intestine. And then they can, image the fine structure of the intestine, for example, or the colon. I guess this is large intestine. I didn't know actually that the intestine goes so far up on the left-hand side, like into your ribs here. Isn't that cool? Yeah. Although actually, after I saw this, I remember that several times I've had burbling in the side, on my side there, and it's something is getting digested. And I always wondered if there was something wrong with me because of that, but now I know it's not. That's just where the intestines go. Anyway, so yeah, contrast agents of various types to deal with the problems of X-rays, not being able to tell the difference between things very well. MRI, totally different technique. I don't know the physics, but okay, so I read Wikipedia and what I understand about MRI is you put a big magnetic field across the person's head or whatever you want. I guess all my pictures pretty much are of heads. Oh, not intestines. So you put a big magnetic field on, and then all the magnetic moments, especially of the hydrogen atoms, line up, or the protons, they line up, and then you whack them with a radio wave, and then they get knocked out of alignment with the magnetic field. And then it's like angular momentum of a spinning top. When you put a top rotating in gravity, it precesses, right? And like the Earth precesses in the influence of the gravity of the moon from 10, 20, or 30,000 period of time. So in the same way, the magnetic moments of this big magnetic field, once they're knocked off the planet, they precess also, and this creates a signal that can be detected with an electromagnetic receiver of some kind, and it slowly damps depending on its magnetic interactions with the nearby materials, like flesh, and it damps at different rates depending on the surrounding tissues. Okay, so depending on like when you look and how you combine all your different exposures and what frequency you knock these magnetic moments off, you get all kinds of different contrast behaviors. So these are 3 different MRIs done in different kind of regimes. You see one of them seems to show. Actually, I can't possibly be bone over there, can it?
No, they're not using it for bone. It's probably for the. Yeah, there's also one time ago for this. We're showing one of the structures of the brain, and the next one you have the other matter, but it's shown better. But it's probably for epilepsy detection or something. They use it a lot. But yeah, you see nicely here. Changing the light. So.
Yeah, no, huge differences. Apparently it's a very versatile technology that you can do different things with it and get different kinds of contrast between different kinds of tissues, so you can do a lot of neat things with it. They have the same, well, I mean, yeah, so there's also contrast agents for this that they can administer things that will alter somehow the magnetic properties of your tissues and then can cause different, different decay to happen and get different kinds of contrast. There's also, of course, a PET scan, positron emission tomography, must be tomography. And on this one, they administer a radioactive tracer, usually like glucose with an oxygen atom removed and a fluorine atom put in its place. And the fluorine is radioactive and it decays to oxygen, so then you have glucose. And this is great because it's biologically active. It goes where, it goes to your brain, for example, like this at the top, because your brain is very glucose hungry. Your body sends glucose there. It also goes to tumors. This person has a tumor in their neck, in the lymph node, I think. So and tumors apparently are very glucose hungry, so they tend to suck up the tracer, and then they're very visible on your radioactive whatever. Oh, another cool feature about this is when they decay, they emit positron, which goes like maybe a millimeter into your flesh, and then it finds an electron that gets slowed down by your flesh, and then it finally gets an electron and interacts with it and blows up, and it emits gamma rays in 180 degrees, except they're not exactly 180 degrees, apparently, because of relativistic effects. They're exactly 180 degrees in the center of mass reference frame, I think, of the positron and the electron together, but that's not your reference frame. It's not the reference frame of the machine. And it's significantly different, so they actually have to not look just for things at 180 degrees apart, but a little bit off in the detectors, which is awesome. So relativity proved by putting radioactive stuff in the, anyway, so these are the main modalities that they talk about. There's a lot of, so they all have different purposes, as you see, and different advantages and disadvantages. This paper is about image registration, multimodality. Registration is aligning multiple images together so that the corresponding pieces are lined up. What you want to do for several reasons. One reason, this is an awesome one. So this is a situation where this is a CT scan, or the output of some kind of CT scan, where they administered a contrast agent to bring out these blood vessels, which you can see in here. So they thought, okay, we'll put this contrast agent in. That's great. We'll be able to see the blood vessels against the neighboring flesh. Marvelous. But it's a CT scan, so we're also going to see all the bone, and we're not going to be able to see the blood vessels very well against the bone. So they thought, okay, great idea. We'll scan them before we put the contrast agent in. We'll scan them after, and then line up the images and subtract one from the other. And then when there's bone in both places, because the person still has bone before and after the procedure, and hopes, that will get subtracted out, and then but the contrast agent was there and then not there, so it won't get subtracted out, and then it'll be visible. Now in the first row, I don't know if they took any effort to line up these pictures or not, maybe just by eye or something, but apparently this is with bad registration. Okay, so they have subtracted in the first row here. It's just not worked out very well because the pictures are not very well aligned. And then if they do proper registration, whatever that means in this book that Henry lending, then they get this effect. This is much more successful. So this is kind of a proof that you would want, that you would actually find it useful to be able to line up the images accurately. You can see the little blood vessels up along the side, which are virtually invisible up here because of the bone. And back here.
There's also the non-rigid registration that they say. So the rigid is that you have only translation and rotation, and then non-rigid is that you allow much more movement.
Oh, okay. And is this, I was going to ask, because this doesn't look like a section. None of these. Is this
No,
like
this is a volume rendering.
Oh, okay.
Yeah.
So, okay,
That you're showing like the 3D model out of it.
Yeah, so this is what the person would look like if you removed
Yeah.
all the stuff that you don't care about. Cool. Okay, but now this problem is somewhat easier than the problem considered in the paper, because in this problem we have two CT scans, and when things line up on this two CT scans, you expect like high intensity in one image to match high intensity in the other, and low intensity in one image to match low intensity in the other, because they're looking at the same things, right? And it's the same modality. In the paper, they're concerned mostly with multimodality image registration, which has the additional problem that there's not necessarily any particular relationship between the two images like that. It's certainly not like there's linearly correlated intensities. They describe briefly, or they refer to a few kind of ad hoc methods of handling that, but as you saw like in the MRI picture, it's not like, there's a lot of different kinds of contrast regimes that you might have. It's not, you don't want to have to design like one for every combination of modality that you're going to have. It's a pain. So this problem I think is much easier. You can just do like minimize the L1 distance between the images or something, and then look at how you want to move the image around to minimize that. Or as they do in the paper at one point, you could lay it out as a intensity histogram. Right? So they will say intensity on one image on x-axis, intensity on the other image on the y-axis, and then at each point there, you'll have like a histogram where the height is the number of pixels, number of corresponding pairs of pixels in the two images that have that intensity and that intensity come from the two images. Yeah. So in this case, because everything should match up properly, you can probably just do like Pearson correlation coefficient or something on that histogram, and everything will be fine. But in multimodality, things are not so nice. So what are we going to do? We're going to do something else. We're going to maximize by mutual information. Well, I should actually, there's another way of doing this, which is you bolt a frame to the patient's head, right? And then you screw it in, and then you scan them twice, right? One and two things, and then you use the frame, the metal frame on their head, to line up the pictures. And another way is you buy a device which does two kinds of scanning at once. These are, I think they have especially like combination MRI, CT scan machines, but these cost like hundreds of thousands of dollars, all these machines. You probably already bought one to do MRI, and you probably already bought one to do CT scanning. So you don't want to just go and buy another machine for no reason. If you can do some math instead. Okay, so information theory. The information theory which is needed is not very much, but I had forgotten all of my information theory, it turns out. So I'm going to review basic information theory in, oh, I missed it. Can I go backwards? No, I might as well go forwards now. Oh, here we are. Okay, awesome. So it's all about conversations. A is sending messages to B, and they're having a nice little conversation about it. So we want to talk about how long messages have to be and how much information they carry. Right, so the main idea is that you carry as many bits as you need to, so the number of bits that you need to send is based on the number of different messages that you need to distinguish between. So in this conversation, apparently A only ever says one of two things. You need 0 or 1, so that is 1 bit thing. But if you had another situation where there were 4 messages that you wanted to send, then you would be doing, you might do this 2-bit code, a 2-bit code in order to be able to send 4 messages, and so on. Yes. So this seems like a reasonable measure of information. Also, it works out nicely that the measure of information is logarithmic in the number of different messages that you might want to send. This makes perfect sense because of what they call in combinatorics the rule of product, I think. Right? So if you send an M-size message and then an N-size message, and this one being a size M, it means you have like 2 to the M possibilities for that part, and 2 to the N possibilities for that part. So altogether you have the product of those, right? 2 to the M times 2 to the N. And this, but you want to say this is like you get the sum of information from these 2 messages, so this makes perfect sense that everything is logarithmic. So you do that. So yes, 2 to the N messages and bits. And if you have multiple, let's say you had 3, this would be a nice example. Okay, now this is a problem. I at this point want to make a binary tree. So I will, this is a binary tree, all right. Tree. I'll just do this, and I'll do some of that, and do 0, okay. And 0, 1 is the child of 0, and then take that and put that down here, and then connect those up. Those are the both children of the parent, and 1, 1, 0, and 1, 1. Okay. About me. So I'm in the habit of heading right after I've done a substantial amount of editing.
File name if you want to.
Yeah, right. Very file. Okay, so here's your binary tree. Now, maybe I only have 3 messages that I never actually want to send, so I'm going to use 1 as one of my messages. I'm going to use 0, 1, and 0, 0 as my other messages. Right, my very valuable file. Right, so you can have codes which have different numbers of bits, 2 bits for this message, and 2 bits for that message, and only 1 bit for this message. VI doesn't, I'm not using my VimRC, so I'm kind of... All right, so, and then if you have, let's say, P sub I is the probability of message I, probability that you will need to send message I, and I is the number of bits in message I, in code word, let's say, code word for message I, then some pi e sub I times n sub I. This is the expected number of bits per message. Okay? And generally we would like to optimize that, right? Minimize that, because we don't want to send too many bits. Bits are expensive. But of course we have this constraint which came up at the top here. We don't, in this model of communication we have to use prefix codes. We have no way of saying that the communication is over. There's no end of message signal. We just send bits. So one thing is we would not be able to say 10 is another code word here after we have 1, because after we send the 1, then when I have nothing more to say, let's say we're sending that message, the person will just be waiting forever to see if we ever send a 0, because they think we might want to be saying 10. So that's no good. So we can't use these two. Once you've chosen them, 1 will be used as one of our messages. So in that way, every choice to use a node in this tree costs you something. It costs you a fraction of the tree which lies underneath it. And how much of the tree it is depends on the length of the bits. Quite straightforwardly, this is 1/4 of the tree. This is 1/4 of the tree. This is 1/2 of the tree. And these are the costs of choosing to have a code word. So the cost of a code word of size ni, let's say of size n, is 1/2 to the n. More or less matches what happened up there. As you see, those two cases that are still in tree. Okay? So optimizing our code, what we want to do is minimize the expected number of bits, subject to this condition, the 1/2 to the n I. Let's put these in parentheses. Those things, braces, should be less than or equal to 1, because we only have one tree to work with. Yes? Okay, so this is our, let's indent this, because it's so important. Okay, so let's do that. What are we going to do? Oh, right, so we will let q sub I be this cost 1/2 to the n sub I, as we said, n sub I. Okay. So really what we're doing is minimizing some p sub I. If we write ni now back in terms of this, it'll be log 1/q sub I, log base 2, of course. So we just convert back to ni's from those qi's, subject to now sum of qi's less than or equal to 1. Costs should be less than or equal to 1. Now it turns out we might as well just assume equality here. This corresponds to saying, well, like back here, like in the tree, if I decide I only have 3 messages I want to send, right, and I can decide, oh, I'll use this code, and that code. Those will be my 3 codes for the thing. There's no reason to do that. You might as well move this one up here. You know? And this corresponds to our assumption, or what I'm about to do, to change the qi into equality. So there's no reason to be wasteful. We'll just say subject to some qi equals 1 exactly. And this is a nice little application of the AM and GM inequality. Hey. How does this work again? Let's see. We take that sum. It's not exactly the sum that we'll take, but I'll take this sum, like that. Okay, so this, of course, the pi's cancel out, and you end up with a sum of qi, so that's equal to 1, which I hope you'll believe. And this sum of pi, so the pi's are the probability of sending message I, right? So they add up to 1 also. So this is a weighted average of these fractions. And weighted average, which we also call an arithmetic mean, is a lovely inequality called the arithmetic mean, geometric mean inequality, which asserts this, that if you run out of space on your screen, you should move down to the next line. Okay, we'll do that. Right, so if you take the multiplicative analog of this weighted average, so multiplying by the pi becomes exponentiating to the pi, and the sum becomes product. You get the geometric mean, the corresponding weighted geometric mean of these things, and the arithmetic mean, geometric mean inequality asserts this inequality between these two things. But let's move on. So, taking logs of that to get rid of products because we don't like logs, or because we don't like products, we'll get what? We'll move that pi in front, and we'll get log. So product will become sum, pi will come down. We'll get log of qi. Let's leave it like this for the moment, and that should be less than or equal to 0 on the other side. Okay. And now let's change this around. We'll take the qi out and so we'll move that out here, 1/qi, and we run out of space again, so we can move on to the next line. Okay, and I'll move this on to the other side actually, like this. Oh, it doesn't fit. Oh, it fits. Hey! Okay. This minus is bothering me. What is going on here? Yeah, I should just kill that, right?
Yeah.
Okay, thanks. Except now they're backwards, so I should write, yeah, okay, I should like this. Reverse. Yep. Normally you would see this written with a minus sign, but I've written one over just to confuse everybody. Okay, awesome. So what this says, remember this was the this was this 1 over 2 to the n. This was n sub I. So this is the length of the code word for message I. This is the probability expected number of bits in the code where we use the QIs. And this says the best that you can do is that. So ideally you would have the length of the code word corresponding exactly to the probabilities that they have, and that's the best you can do. Maybe you can't always do that depending on the exact probabilities, but whatever. Which is exactly what we have upstairs. Back here, indeed, this was the ideal code. If the probability of the message, which is 1, is a half, and the probability of the other 2 is 1/4, this is exactly what you should do. So says Huffman. Okay, so this is so far so good. This is entropy. In fact, we'll call this, this expression. So we have a random variable. Let's call it p or something. It's not called p. It's called a. Is this expression, sum of pi log 1 over pi, so that where the pi's are the pi are probabilities of the outcomes of the random variable a. I'm not going to worry too hard about doing proper notation here. Okay, so that's great. That's optimal coding. These two things also have names. Say this is this h sub a is called entropy. Say the PI, or self-information, some people call it, depending on your exact context. And this thing here is cross entropy of PI and QI. And to get the difference between them is called the Kullback-Leibler measure, or Kullback-Leibler divergence. So if you were, right, so on the left-hand side we have the optimal code, so the expected number of bits for the optimal code for this situation. On the right we have the expected number of bits if you use these other lengths, the ones that correspond to the QIs. So the difference between them is kind of the cost of not using the optimal code. And it's the amount by which the distribution that you get from the QIs. So if you use a code which is optimized for the probabilities QIs, this is, but you use it for things that have the PIs, this is the cost, the difference between these. That is the basis of the mutual information measure. Well, let me first do it as, so let's do, which one do I want to do first? Okay, so let's do this one. I don't know if this is right. So this is mutual information, to define it. I'll define this in a second. So HA is the same thing. So we have 2 information sources here, or 2 probability distributions. This is the entropy of the one, and this is the entropy of the other. And this is the entropy of the joint distribution. So you just take the events where A has a particular value, B has a particular value. Those are the events of the joint distribution, the probabilities. So what's going on here? Let's get back to the application, image registration. So you have image A and you have image B. One of these random variables proceeds as follows. You pick a random pixel from image A, and then you determine the intensity there, and that's the message that you send, the intensity value of that pixel. Okay, so that gives you a random variable, or a messaging regime, and this is the expected number of bits in that kind of in that messaging regime. So if you want to express intensities from image A, this is how many bits you need to do it on average. If you're going to do the same thing from image B, pick a random pixel and then report the intensity that you cost it. What you do here is you pick one pixel, but the corresponding pixel from the 2 images, and you get the intensity from A and the intensity from B, and you send both of those. There's a message that reports both intensities. So, of course, you could do that by just saying, well, I pick randomly from A and from B, I'll send a message for A, I'll follow it up with a message from B, and that'll be the whole thing. And if you do that, you'll spend this much on average. Because you send a message for A, you send a message for B. If you do it optimally for the project where you send both of them at once, you'll only spend this much. So if there's a difference here, it's because A and B share information. Because they're correlated in some way or dependent in some way. And this measures exactly how many bits you save, and how many bits of information there are common between A and B. So rather than sending A and then B, you you can send kind of stuff about A and then stuff about both of them and then stuff about B, conceptually. How your code actually works is a whole different story. So that's the mutual information, and they point out in here that if you get a good if you play with these formulas a little bit, you can show that it's one of these expressions for information. What do I want to say here? Oh, let's say this is kind of awkward. Let me. I'll just do it the way that they do it, and then we'll complain. A B, back here, put a comma in here, and then run out of space. So let me go to the next line. Log of this divided by B of A and B of B, and then run out of space again. Okay. Let's just go down. Okay. Okay, so this is an expression that we had above. It's this minus that. Okay, so it's the cost of using the wrong code for a particular communication task. Right? And the code that we are using here is the one which has probabilities like this, which are just the product of the probabilities for A and the probabilities for B. So treating them as independent, and you get some code, which is like this code, essentially, by sending just A and then sending B. And if you use that, instead of using the actual joint distribution, which is here, then this is the divergence. This is how much you lose by doing that, and it's the same. So it comes out the same as this. And it's exactly this expression over here. So this is what they minimize in the paper. They take their two images and just move one of them around until they minimize this expression. There's a couple interesting other little details about interpolation and stuff. No, this is 30 minutes, maybe that was. Okay, so they do some interpolation, nice little interpolation trick. One of the problems is, especially with like rigid notions, right? You have the two images that you're rotating, and then let's say you rotate one of them to see if that's a better alignment, right? Then the pixels probably don't line up anymore. Even if they did to begin with, and maybe they don't because they were different machines or whatever, right? So the pixels don't line up anymore. What do? How do you check like what the corresponding pixel is? So they do an interpolation trick, and they've got a few different interpolation methods in here, which are pretty cute, I think.
I'm subscribing to two of them. So.
We are? Okay, so Mary will be speaking about that in a few minutes. This is like we planned it. Yeah, okay, so then I'll not talk about that. And they also have, okay, well, the way they talk about it so briefly, I assume it's just a standard method for them. Powell's multidimensional direction set method. This is a very clever thing. No, nobody's ever heard of it? I never heard of it either, but they talk about it in paper, they just cite it, and they just move on. Powell's multidirectional direction set method. So this is a multidimensional optimization technique where you're not able to compute derivatives for some reason, or you don't want to, you don't even want to approximate them. So what they do is they just optimize. First, they optimize over a line. Right? They have this multidimensional scalar field, right? Which has a minimum somewhere over here, let's say, and then they just start somewhere, and then they take like a line in the x-axis direction, and they optimize over that first. They just by searching somehow. And so they find the spot that they should go to. Turning towards them. So they find the spot that they should go in the x-axis. And then having found the minimum in that direction, now they go in the y-axis direction. And then they find the minimum on that line, and then they go there. Now you could just iterate this, right? Go then optimize on the x-axis, and optimize on the y, and hope that you end up in the minimum. And that would be great. But what they do instead, which is kind of cute, is they say once you've done this twice, or however many dimensions you have, 6 times in the 6-dimensional space, and you found you've found some, how to say this, the total operation that you did in moving x direction, y direction, and z direction, all of those all together, that looks like a pretty good direction in total, the vector sum of all of those. So they say throw away the x-axis direction and replace it with this direction, the direction that you went. And so in the hopes that going in that direction is going towards the minimum. Okay, and then do the same trick again with these set of directions, this direction that you just computed, and the y and the z. And then you do that with these 3 directions, and then you get some new direction, and you throw away the y, and you replace it with this new direction, and you keep doing it like this, right? Hoping over time to generate like a linear basis, which will be appropriate to the problem at hand. Obviously, this makes a lot of assumptions about the overall structure of the scalar field, but apparently it is useful and standard enough that they can just mention it, cite it, and move on. So they do that, and they get some results. They did it on an RX 6000. This was in 1997. I had one of these. Not myself, at work, we had one. I was so thrilled to see that they were using RX 6000. It took them like anywhere between 2 and 40 minutes to do one of these things where they optimize the image alignment in 1997, so I assume it's faster now.
Yeah. But actually the image is also maybe resolution becomes bigger, so you have more voxels, so but it was a few minutes rather than few to do it. So.
Okay, so that was it. That is I'm talking about the image registration. And works, that's the conclusion of the paper. It works.
Yeah, it says sub-voxel accurate, so that means like and less like a voxel is more like 0.2 millimeters, 0.5 millimeters, so it's smaller than that size. So
Yeah, their interpolation methods are quite slick, so they can actually be sensitive to differences that are smaller than the resolution of the images. Very, very slick.
It's definitely important. For example, if you would measure is tumors shrinking over time, and really the measurement flow that you have, like aligning the tumor needs to be indeed is then bigger than how you're registering your images. So it's pretty important.
Yeah, if you actually want to know that you're having some effect.
Yeah.
Which is nice.
And also for your radiation treatment, it's also important that everything is nicely aligned. Otherwise, you're also too much tissue.
I love this line. In radiotherapy planning, dose calculation is based on the CT data, while tumor outlining is often better performed on the corresponding MRI scan. I didn't quite understand why that was the case. Is this because the dose calculation depends on the thickness of the bone?
Yeah, because your X-ray need is, or your radiation is much more attenuated by the bone. So.
Yeah, so they have to know the thickness along the path that they're going. Yeah, okay. So, yeah. That's a paper.